Alright, so let's pick back up where I was in the last video. So, yeah, I was right. The integral was 0. And one of the ways you could see that, in I think sort of a natural way, is just to look at the fact that when the, what's this thing called? Is it the radicand, or, I don't know. Anyway, the input to the square root, excuse me, fifth root, 1 minus 2x, well that's 0 when x is equal to a half. And so what's going on here is, like, it's symmetrically half above and half below the x-axis, between 0 and 1/2 and 1/2 and 1. Here's an explicit change of variables that shows this. So if you let w equal to x minus 1/2, well, dw is dx, and if you change 1 minus 2x to w's, you got minus 2w. So this integral from 1 to 0, the fifth root of 1 minus 2x dx, becomes the integral from 1/2 to minus 1/2, the fifth root of minus 2 w dw. And, well, by that, basically we have an odd function of w integrated symmetrically about 0, so it's 0. So that's, I was kind of happy with that. Anyway, okay, so next few examples planned out for us here. Let's start with this one. The integral from 0 to 1/2 of the square root, 1 over the square root of that. So the antiderivative of that is the inverse sine of x. Alright. Fundamental Theorem of Calculus Part 2 says I have to evaluate from 0 to 1/2. Alright, so that is inverse sine of 1/2 minus the sine inverse of 0. Now, inverse sine of 0 is 0, because sine of 0 is 0. And the inverse sine of 1/2 is pi over 6. So the answer is pi over 6. So you might remember sine of 30 degrees is 1/2. Anyway, there it is. Alright. This one, integral from 0 to 1 of that, well, this is inverse tangent, right, of x. That's the antiderivative of 1 over 1 plus x squared, integrated from 0 to 1, evaluated from 0 to 1. So I have inverse tangent of 1 minus inverse tangent of 0. Well, inverse tangent, oh my goodness, inverse tangent of 0 is 0. Right, just like inverse sine, because tangent of 0 is 0 and sine of 0 is 0. And inverse tangent of 1, well, that's pi over 4. Alright, because of course, you know, the tangent of pi over 4 is 1. Alright. And this was because we happen to know that the sine of pi over 6 is 1/2, or in terms of degrees, the sine of 30 degrees is 1/2. Of course, technically it's a different function. It's the sine in degrees function versus the sine in radians function. You know, you have to change modes on your calculators to access those different functions, right? And then, well, more commonly we agree that the context tells us whether we're using sine in degrees or sine in radians. Okay, so cosh of 2x dx. Well, the antiderivative of that is 1/2 the sinh of 2x. Alright, you're making a u equals 2x substitution. And then now I got to evaluate that thing from the natural log of a to the natural log of b. Of course, we're assuming that a and b are positive constants here. So that is going to give us 1/4, right? E to the 2x minus e to the minus 2x quantity evaluated from log a to log b. Alright, so what is that? Well, that, right, is equal to 1/4 of, let's see here, we got e to the 2 log b minus e to the minus 2 log b minus 1/4, right, e to the 2 log a minus e to the minus 2 log a. Alright, so using properties of logs, this is 1/4 e to the log of b squared minus e to the log of 1 over b squared. Sorry, it's getting a little bit small. And then minus e to the log a squared, minus gives me plus, e to the log of 1 over a squared. Because if I bring the minus 2 inside, it's a to the minus 2, which is 1 over a squared. Sorry, it's getting kind of tiny. And then that is 1/4. Let me just final answer here. So that's 1/4 b squared minus 1 over b squared minus a squared plus 1 over a squared. And that is the answer. Now, of course, you could have written your answer in terms of sinh of natural logs, but I do believe this is the simplified answer, right? This is, I think, the best answer. Well, I mean, best is, I don't know. Anyway, well, something is very funny in the kitchen. All right, so let's see here. And then one more example here. The integral 2 to the x from 0 to natural log of 3. All right, the integral of 2 to the x is 2 to the x over the natural log of 2. All right, that's the antiderivative of 2 to the x. Now I have to evaluate that thing from 0 to the natural log of 3. Okay, so I'm going to make myself a little edge of the example line. All right, so this is equal to 1 over the natural log of 2, and then that's 2 to the natural log of 3, minus 2 to the 0, which is equal to, let's see here, well, I mean, we could leave it like that, I suppose. Let's see here. I mean, that's sort of one answer. 1 over the natural log of 2 times 2 to the natural log of 3, right? Minus 1. Now, let's see here. Can I do better? Well, the natural log of 3, right? Well, that's not the way I want to go. 2 to the theta can be rewritten as e to the natural log of 2 to the theta, right? Which is e to the theta times the natural log of 2. So in other words, this is 1 over ln 2. 1 over ln 2 times, I can trade 2 to the natural log of, basically theta equals natural log of 3, right? So I can do, I can rewrite this as e to the, sorry, I lost my place, natural log of 3 times the natural log of 2 minus 1. So, I don't know. Is that better? Probably not. Of course, you could bring one of the natural logs inside and make it like e to the... Oh, that's what I wanted to do. I'm sorry, I'm an idiot. 1 over the natural log of 2 times e to the... Let's see, let's pick one. How about natural log of 3? So I'm bringing the natural log of 2 inside using properties of log. So that's natural log of 3 to the... This is stupid. E to the natural log of 2. Alright, minus 1. Which, I don't know, I guess it's not much better. It's funny. So it looks like I've got 1 over ln of 2 times 3 to the ln of 2 minus 1. It's funny. Is that true? Is 2 to the ln of 3 equal to 3 to the ln of 2? Oh, yes, of course, that's pretty obviously true. If you take the log of both sides and use properties of log, this is equivalent to log 2 times log 3 is equal to log 3 times log 2. So, anyway, long story short, my quest for simplifying this has led me to nowhere in particularly interesting, and I'm going to call this the answer. Alright, anyway, there you go. So, I think that's a pretty good slice of definite integration. I'm going to switch over next video to the problem of calculating areas bounded by curves, and then on to volumes and other applications of integration that you might typically see in Calculus 1. Thanks, guys.